Right, this diagram shows the speed of sound experiment. What you have here is someone clapping at a start microphone. So you clap at start microphone. And when you do that, that starts connected in this circuit here. You don't need to know the ins and outs of it, but what you do need to know is it starts a timer. So it starts an electronic timer. And then whenever the sound travels through the air, so sound travels through air, to the stop microphone, and whenever it hits the stop microphone, then that stops the timer. And then the last bit you would have to describe is how you actually calculate the speed of sound. And this uses the equation speed is distance over time. So speed is distance over time. So you'd measure the distance with a ruler. You've got your time. If you're being a very good scientist, you should of course repeat your timing 3 times and take an average time. So your electronic timer has picked up your time for you. And whenever you put those values in, then you will end up with a speed of sound. So I think in this table, this is how you record your results. So your distance, the one in the classroom that we did, their distance was 4 meters. And the time comes out to be in around 0.012. I'm going to make up a couple of these. So you can do a wee calculation now if you want. 0.011. So you do a calculation there, stop the video cast and calculate an average speed. So the average time there, if I just do a wee calculation, divided by 4, is 0.012. So the average is 0.012 seconds. And then the speed is equal to distance over time, which is 4 over 0.012. And that gives you 333.3, or repeated 333.3 meters per second. And this is a very common value for the speed of sound at room temperature. You'll find the speed of sound being quoted at room temperature somewhere between probably 320 up to 340 meters per second. And in the question, you always have an idea of that. In a question and exam, they will give you a value for it, or else they might ask you to calculate a value, and whenever you come out with your value, you'll know you're more or less right if it's 300 and something, roughly in that range there. Now, sound not only travels through air, it also travels through lots of different types of materials, including solids, liquids and gases. You know it travels through liquids. If you're under the swimming pool, you can hear noises above you outside. If you know it can travel through a solid because you can hear somebody knocking on the door to you if you're in a room and they're outside the room. So the speed of sound changes and the speed of sound for materials changes depending on their density really. And objects which are more dense, their particles are closer together and therefore the sound can travel much more quickly through them. So we know already that the speed of sound in air is about 340, so that's the air. And we know that carbon dioxide then is going to be something which is a little bit around that same kind of value. And so carbon dioxide must be the 260 here. We're left with aluminium, glass and water. Water is a liquid. Its particles are closer together than carbon dioxide or air, but not as close as it would be in something like glass or aluminium. So water must be the 1480. So you have 4540 and 6420 left. You would imagine that aluminium is much denser than glass and its particles are closer together. So we'll assume this last one's aluminium and therefore the 4540 must be the glass. Just to go back here a minute, this experiment for the speed of sound in air is also the same experiment for the speed of sound in a material. Now we found this very difficult to do in the lab because our timer wasn't sensitive enough and we needed a very tiny time recorded here. and our timer just couldn't do it. But what you would do, if you wanted to do this in a solid, you would clamp your microphone face down onto the bench and onto the bench or the solid that you wanted to pass through. So if we did it on our wooden bench at the side of the room, we would have these two microphones clamped, and you would make a little tap on the bench, and the stop microphone then would stop whenever the tap has reached down to the stop microphone through the bench. And so it's the same experiment. So just be aware of that in case you're asked to maybe describe it. So just a wee bit more about sounds and different states of matter. Sound waves need a substance to pass through. What are all substances made of? They're made up of atoms and molecules. What is a particle solid of a liquid and a gas? A solid, liquid and a gas. So a solid, the particles are closest together, and in a gas the particles are furthest apart. And that of course means that sound is going to travel much more quickly through a material whose particles are very, very close together. So sound waves travel by particles vibrating. What state does sound travel fastest through, and why? The answer is a solid, and the reason is because the particles are closest together. So sound and light, which is fastest. During a thunderstorm, thunder and lightning are created at the same time. Which do you notice first? So you see the lightning first, of course. And the reason is because light travels much faster than sound. Now, the sound is actually made by the light. As the electricity passes to the ground, it rapidly heats the air around it, and it heats it to something like 5,000 degrees C. And that rapid heating causes expansion. And you know when things expand, like when you put ice into water, the ice expands very rapidly and it cracks. That's exactly what happens in the air, only it's so hot that it causes this massive boom. And that's what thunder is. And it rumbles on for a little while because it reflects off the ground and the clouds and so on, and it rumbles maybe for a little while. But that's exactly what the thunder is. It's just the sound of the air expanding as the electricity passes through it. So light travels at approximately 300 million meters per second, where sound is 320 meters per second. So you can see approximately that light is 1 million times faster. And it's worth keeping that in your head. It's about 1 million times faster. Okay, if you can travel faster than the speed of sound in air, then you've broken the sound barrier and there will be a sonic boom. So we're just going to do a wee quick question here. Speed is distance over time. And therefore we're going to do a calculation. So 600 divided by 5 gives you 120 meters per second. So the small airplane's not going to break the sound barrier. The jet fighter, 900 divided by 2 gives you 450. So it is going to break the sound barrier. A cheetah, 50 over 2.5, and 50 divided by 2.5 gives you 20. So it's not going to break the sound barrier. And a meteorite, 10,000 divided by 0.35, and it definitely is going to break the sound barrier. 28,571 meters per second. So the two that are going to break the sound barrier are the jet fighter and the meteorite.